Hello everybody, and welcome to this EDU Onyx project on data compression and visualization using principal component analysis. My name is Brendan, and I'm going to be guiding you through this project today. As always, we are going to be using Python and working in Jupyter Notebooks to bring this project to life. So let's go ahead and dive right in and see what this entails. To start, I'm going to open up my terminal. I am working in Windows once again. So if you have a Windows machine, you can follow along exactly. If you are in a Mac OS or a Linux machine, there might be some slight differences, but that's okay. Opening up this Jupyter Notebook, we'll go ahead and open that in the tutorial directory. So just Jupyter Lab. I'm going to be using the Jupyter Lab version of Jupyter Notebooks today, since it adds on some nice handy features onto just the notebooks themselves. All right, so here we go. Here's my Jupyter Lab. Right now, my tutorial folder is once again empty, so I don't have anything in there. But I'm just going to open up a blank Python default notebook. I'm running Python 2.7, but we'll see that in a sec when we start importing different libraries. All right, so let's go ahead and get started by naming this something appropriate. Today we're going to be doing principal component analysis, so PCA. So we'll do PCA Viz because we're doing a visualization as well as compression. All right, just a little tidbit before we begin what we're going to try to accomplish in this project. What we want to do is use principal component analysis to perform data compression and visualization. For this purpose, we are going to be using the well-known IRIS dataset, which contains 3 classes of 50 instances each, 3 different species of flowers. We're going to try to be classifying them as such. For this project, we are going to be using k-means clustering, and this is where the compression and visualization comes in. For this dataset specifically, there are 4 different features which we will see when we import it. And you can't exactly graph or visualize 4-dimensional objects. We're living in this 3-dimensional world. XY plots are 2-dimensional. So that is what we're going to use the PCA reduction for. We are going to compress our data into a 2-dimensional feature set that we will then be able to visualize through a normal XY plot. So let's go ahead and get started with that. So first things first, we need to import some libraries here. And as well, this is going to ensure that we have everything installed appropriately and that we are all on the same version numbers. If you have more recent versions than I do for some of these libraries, that is okay. You shouldn't run into any issues unless some of the functions get deprecated. But in general, as long as you have these installed and ready to go, we should be just fine. I'm going to print off the version numbers here. So for example, Python will print off the sys.version. This is going to be the 2.7. Spell this right here. There we go. So we'll also print off the pandas. Dot format. As always, I'm using the dot format to substitute into these strings that I'm printing out a variable. In this case, the variable is a version number. So NumPy. And you also might notice that I imported these with the namespace PD for pandas and NumPy as MP. That is a pretty standard import namespace for both of these libraries. It just makes it a little quicker to type out. It's really not necessary, but you'll see it a lot in practice. So I like to replicate common practices in these projects, so that is why I'm doing it here today. All right, here we go. Last one, dot format matplotlib, which we'll be using for our visualizations. Version, there we go. All right, once we have this done, you can click the run button up here, or more simply, just do Shift Enter, and that'll run the cell. Make sure all of these are imported correctly. And then we will get going into importing and pre-processing the IRIS dataset. So we'll explore that a little bit and see what it contains. The IRIS dataset is commonly used for pattern recognition tasks As a result, it's going to be available directly through scikit-learn, which is very convenient for us. And there we go. Our libraries are all imported. Like I mentioned, Python 2.7, then Pandas, NumPy, scikit-learn, Matplotlib. These are the versions that I am using here today. All right. So the Iris dataset available through sklearn or scikit-learn, because it is so commonly used, we can simply say from sklearn import datasets, and then we can load it directly. So load dataset. I have a comment here for readability. We'll say Iris. That'll be the name of our dataset. Datasets.load Iris. A parentheses here since this is a function. And this is actually going to load in our dataset. So what we can do is we can separate out our features. So iris.data. We can separate out our target, which is like our class label. So target equals iris.target. That's going to be the species label for each of these data points. And then using these, what I want to do here today is I want to generate a pandas data frame from these, simply because it gives us some nice features such as descriptive statistics and different visualizations that we can use to better understand the data before we dive into the actual machine learning. So what I'm going to do is create a data frame out of these features. Right now it won't have any column names, but I can add to it columns. And we actually have these feature names already stored in our Iris dataset that we loaded in from sklearn. So there we go. We have our data frame. We have our dataset loaded. If we go ahead and run this, there's actually not going to be any output from this cell currently, but it's finished there. So we have the dataset in. Let's go ahead and actually print out maybe some of these targets and target names so that we can indeed see that it was imported correctly. So we also have the target names. We print these out. So here you see we have 150 instances in these 3 different classes denoted 0, 1, and 2, which correspond to these 3 species of iris flowers. So the Setosa, versicolor, and virginica are our 3 species we're working with here today. So just 150 instances, and we actually see those, we put those into our data frame. So if we print data set information, we can simply do print dataframe.shape. We can also do print dataframe.head. We'll print off the first 20 data points in this data set or in this data frame. So here we go. Here's the first 20 data sets, and here you see our 4 different features, such as petal length and petal width, sepal length and width, as well as our other one, both in centimeters. You see these nice, it includes units and stuff because we got this directly from the Iris feature names up here above. Those were our column names. You see our shape, we have 4 different features for, that's our 4 columns here, and then 150 instances. You see all 150 of those up above. All right, so we've got our data set. The Iris dataset, so common, so easy to use. It's built directly into sklearn. So that is quick and easy to get going. One other thing that we can do, or we'll do a couple other things actually with the data frame, is we can print dataset descriptions and class distributions if we would like. And we can do that by simply saying print dataframe.describe, and then a parentheses. This is a function on the end here, so we need parentheses. We have these convenient descriptive statistics about this. This is going to be less important since we are using a well-known and relatively small data set here today. However, if you didn't understand your data as well, this dataframe.describe would be a very valuable and very useful function that would help you get to know your data set before beginning to try and apply different machine learning algorithms. The better you understand your data set, the better you're going to be able to choose which approach and which algorithm you want to use. So statistics like these can be very helpful. Furthermore, we'd be able to tell if we have missing values or something like that. Since our minimums here are all defined, it looks like we don't have any missing values, so that is good as well. We have a count of 150 for all 4 of these different features. So every instance in our data set has all 4 features, so we're good to go there. Some other cool things you can do with the data frame, and we're going to use pandas.plotting for this. We want to import the scatter matrix. And then import matplotlib.pyplot as plt. Pyplot, we need an L in there. There we go. So if we import these, we can display a scatter plot matrix of all 4 of these different features very easily. So we can simply say scatter matrix data frame and then plt.show. This scatter matrix is a pyplot. So we can simply call plt.show after that and we'll pull it up. So if we run this, it's going to take a sec because it has to import these different libraries and packages as well. But this gives us another method to analyze our data set. And here we see our scatter plot matrix. We have all 4 features plotted against each other. This is actually kind of small. It's a little bit hard to see since these are running together. But you see we actually have some pretty good linear relationships between some of these different features. So this gives us a better understanding of perhaps we have a linear basis to our data, which makes sense. Petal length and petal width are obviously going to be related probably linearly, and that is indeed the fact that we see here. Since these aren't just randomly distributed, we see pretty distinct clusters here between like petal length and the sepal length and sepal width. We know as well that this is a good candidate for a clustering algorithm or a different classification algorithm as well. You would probably be able to achieve higher accuracy percentages on this if you were to use a deep neural network or simply a even simple neural network as well. Would probably do a very good job of classification. However, we're going to be able to get decent results via clustering because there is pretty good separation here as well. So again, not entirely important since we already have a pretty good understanding of this data set. It's well known, well used. However, rarely in the real world are we doing machine learning on well understood data sets. Real data that you might be working with at your work or whatever application you are using is not going to be this pretty. You're going to have missing values. You're going to have outliers and other things that you need to account for in pre-processing before you actually deploy your machine learning algorithms. Okay. Now we are going to move on to the elbow method. So the elbow method is something that's used very commonly with k-means clusterings. The k in k-means clustering, remember, refers to the number of clusters that you're going to use. We have 3 species of flowers in this data set, so it's pretty easy to say, all right, we're probably going to want 3 clusters. However, what if we didn't know how many species we had? After all, this is an unsupervised learning approach, so we don't have, generally, we're not going to have the class labels for all of our data. So determining the number of clusters is going to be an important first step, and it's something that we can do with the elbow method. So let's take a look at that and see how you actually go about implementing the elbow method for k-means clustering. So let's say elbow method to determine optimal number of clusters. And again, not important necessarily for our data set here today, but a very valuable skill to know when you take this information and apply it to your own applications, and that is why we are going to use it here today. So first things first, I want to import sklearn.cluster import k-means. This is the k-means algorithm that we're going to be deploying today. Next, I want empty x and y data lists. And so we'll explain why we need these in a second, but a list in Python, remember, is just a bracket, a straight bracket. So X, that's a blank list, and then Y, a blank list here as well. All right. And now, so what we want to do is we want to loop through a variety of different number of clusters. So starting at, let's say, 1, and then we have 150 instances, let's say about 30 clusters. So to do that, we would say for I in range 1 to 31, this is non-inclusive, so this is just going to be 1 to 30 here, this range. So we'll test it for all these different number of clusters. We'll initialize and fit the k-means model. So k-means is going to equal k-means, the instance or the package that we imported above the class here. K-means, and then number of clusters we are going to define as I, the 1 through 30 that we have in our range. So k-means.fit, and let's fit it directly to our data frame. This is a nice feature of data frames. You can pass them directly to sklearn without further processing. So just another reason, if the descriptive statistics weren't enough, to format your data as a data frame. So there we go. We fit our model. Next, what we want to do is we want to first record the number of clusters. So to do that, I'm going to append the number of clusters to the X data list. That's pretty simple. With a list, you simply type the list name, so x.append, and this is an integer, just I. All right, so X is going to be our number of clusters, and this is going to be a visualization through matplotlib. So it's going to be a plot. The X is the number of clusters. The Y is going to be the average within cluster sum of squares. And this is going to be the inertia. We've talked about the inertia in a clustering or a k-means clustering before. This is going to be averaged over the 150 instances. So we get an average within cluster sum of squares instead of a total within cluster sum of squares, which would be the inertia. And that is actually going to be our Y data point. So we want to append the average within cluster sum of squares to Y data list. Before I go on, we don't really need to see this over here. So if we simply type Control B, we can minimize that, give us a little bit more room to work with. Okay, so the average within cluster sum of squares is going to be equal to k-means.inertia, and remember the inertia here is the total within cluster sum of squares. So to get the average, all we have to do is divide by the data frame.shape 0. This is going to be 150, since we have 150 instances in our data set today. So y.append AWCSS, average within cluster sum of squares. All right, so I'm going to start this. It's not going to take too long, but we can actually move on to the visualization. We'll start programming this as it runs. It's going to be pretty quick since we only have a 150. Oh, in fact, it's already done. Wow, that was actually even faster than I anticipated. If you have an exceptionally large data set, maybe a couple tens of thousands of data points, you're going to probably want to use the k-means mini batch to do this. It's just an initial testing at the start. Since we only have 150, wow, that went very, very fast. All right, so we want to import matplotlib.pyplot as PLT. We'll use the namespace PLT here today. And so plot the X and Y data that we just generated. So plt.plot X, Y, and we're going to label it. We'll do blue O's, and we'll actually have a line in there as well. So that's just a formatting. And then plt X limit. Make our plot look a little nicer here. The 1 to 30 clusters. plt.x label. Number of clusters. plt.y label. It's going to be our average within cluster sum of squares. There we go. So there's that. There's the Y label. Let's give it a title. Titles are good. K-means clustering elbow method. And we'll see in just seconds what this elbow is referring to. So let's display the plot. it's PLT, so you got to remember to call plt.show. plt.show. There we go. That'll bring it up. Run this. And here we go. So here's the elbow method. On our y-axis, we have our average within cluster sum of squares. On our x-axis, we have our number of clusters. And you see this elbow type shape. And this is a very nice one. It works great for this data set since it's pretty well defined. At the start, when we go from one cluster to two clusters, you see a dramatic drop in the average within cluster sum of squares. When we go from two clusters to three clusters, there's another fairly dramatic drop. As we move on from that, we start to approach an asymptote, and we actually start to level off where increasing the number of clusters doesn't reduce the average within cluster sum of squares by any significant amount. And that's why you see kind of this asymptote here down at the bottom. So where this starts to become linear, it may not necessarily be strictly horizontal. However, because ultimately you're going to have an average within cluster sum of squares of 0 if you have a total number of clusters equal to the total number of instances in your data set. So this isn't a true asymptote. However, it is linearly related approximately down here in this section, and then you have a sharp bend and a steep slope up here, steep negative slope. So right here, this is a cluster number of 3, and this is right on the elbow. So this is confirming what we already knew before. 3 clusters is probably going to be the optimal number of clusters to use for this particular data set. You see this is increasing. 3 to 4, there is a drop in the average within cluster sum of squares. It's not that significant. We still might, perhaps one of the species of plants has 2 very different characteristics, groups of clustering. So you might get some benefit from going from 3 clusters to 4, but in general, there's not going to be a huge reason to move past that number 3 there. All right, so this is the elbow method. We have confirmed that indeed we want to use 3 clusters for this data set. Makes sense. We have 3 different species here. We have the Ceratosa, the versicolor, and the virginica, 0, 1, 2. So we are good to go. All right, so we can move on to principal component analysis. Well, we're actually going to do that in the next video just to keep these short. So keep listening. I hope you enjoyed learning about the elbow method. It's actually really useful, comes in incredibly handy if you don't know how many clusters or how many classes even you have in your data set. So I hope you've got some value from that. Our data set's all set up, imported from sklearn, and we're ready to go in the next video. Thank you very much.